This collection of slides is a short introduction to the results of 30 years of research and development to achieve a standardized method for communicating digital materials and property information between different engineering software systems and for the conservation of this data over long lifetimes. The flow of material and information over the whole product lifecycle is illustrated in this image, and all of the stages have an interaction with the wider natural environment. In red, it is shown the flow of materials, while the information flow is in light blue. Several strategies have been tried to achieve the interconnection between different software systems to enable this flow of information. Individual one-to-one translators is a software solution that is not sustainable over multiple connections, and also when future connections will not be known. Native file transfers can be imposed on suppliers by large organizations, but the costs to the suppliers is considerable and requires frequent updates of the systems to ensure compatibility. The global solution is to adopt a neutral representation of the information that is also digitally processable to achieve a complete description of the information that is needed for an engineering application in a particular part of the product lifecycle. Each system then needs only one interface to the neutral representation to achieve full connectivity. For any communication that is understandable, there needs to be a mutually accepted structure for the information items and explicit rules for how these items shall be interpreted. The grammar. A rigorously defined information model can provide these benefits, and if the information model is written in a computer processable language, then it can be digitally processable. Effective information representation relies on 4 key components: data items, words or numbers, clear definitions of their meaning, an information model to interpret their structure, explicit rules for how they must be represented. The information models for the digital communication of engineered product data have been developed over 30 years of fundamental research and development by the members of the TC 184 SC4 Committee of the International Organization for Standards, known as ISO. The slide illustrates the extent of the global collaboration and financial support that has been directed at this achievement over more than 30 years, and that is still in progress as new engineering and manufacturing requirements emerge and new digital technologies appear. The technology was developed by world-class engineers for engineers and is commonly identified by the acronym STEP, Standards for the Exchange of Product Data. The main standards are identified as part numbers of ISO 10303, Product Data Representation and Exchange. Part numbers 40 to 60 provide an integrated fundamental model for all generic engineered product data from which all applications of the generic model to specific industrial requirements are derived. These application models, AP, parts 200 and above, are what are incorporated in the software appropriate to the engineering application. Material information and the data related to materials science and engineering can be included in this STEP technology by recognizing that all materials in practical use are products produced by a process. There is no justification for treating the material in isolation from the finished manufactured product. They are both contained in the same shape and dimensions, and they have both been through the same manufacturing process. A property is a response of the product to its environment, and so the semantics of the property value will depend on the semantics of this environment. Weight is a response to the effect of the local gravitational force on the mass. The length of a long metallic bar will depend on its temperature. The strength value from a uniaxial tensile test depends on the speed of the elongation. The environment for a corrosion property value needs to be specified. Therefore, the value could depend on a collection of factors, and this collection is identified as the data environment for the value. ISO 10303. Part 45 is the part of the generic fundamental model that specifies the representation of a property and its value, when the property value depends on the collection of factors in a data environment. This is a necessary requirement for all materials, property data. Several other ISO 10303 standards also use the representation of an engineering property as defined in ISO 10303 Part 45. Manufactured products may not be in a convenient form for testing, and not all of the items in a batch of products will be tested for quality control and quality assurance. Therefore, there needs to be a process, Step 1, to select for testing a sample that conforms to a specified procedure. A manufacturing process, Step 2, may be needed to transform the sample of the product into a specified shape for use in the testing method. Step 3, such as a uniaxial tensile test or the measurement of fracture toughness. The outcome of the test should be evaluated, Step 4, to confirm that the test process was valid. The results of a series of tests may be processed, Step 5, to provide a reduced value, such as a mean and standard deviation for reporting purposes. Testing procedures are usually specified by a quality manual, and therefore the whole sequence of processes should be evaluated, Step 6, to confirm that the requirements of the quality control process have been satisfied. The approved data resulting from this evaluation may be entered into a test certificate that would accompany the product for the assurance of the customer, Step 7. Measured values from a testing process may also have to be further processed to determine the values to be used as a basis for design values, Step 8, and the constraints on the use of these values have to be determined for the design allowable, Step 9. The main concept of ISO 10303 Part 235, AP 235, is that the semantics and value of an engineering property are determined by the results of the processes used in the test method. A P235 extends Part 45 to be able to record these processes and, so, provide an audit tail for the derivation of the value, if a later forensic investigation is needed. The main discovery in the development of ISO 10303 Part 235 was that all of these processes could be represented by the same information model structure that is defined in ISO 10303 Part 49, Process Structure and Properties. A high-level view of this information structure is shown in this slide. So, each of the different steps in the testing of a product can be represented by instances of this information model. This slide illustrates the main features of AP235. Note that the processes could be manufacturing processes, and so AP235 could have a wider application than just for testing. The full scope of concepts and values that can be represented by AP235 are identified in this slide. Among the technical concepts we find product and product history, properties, processes, process resources and properties, numerical and descriptive values, mathematical expression values, uncertainty and reliability of all values, product substance composition and internal structure, dimensions and tolerances. Among the administrative concepts we can mention dates, times, persons, organizations, addresses, approvals, qualifications, certifications, documents and files, effectivity, external references, languages, locations, requirements. an essential component of effective communication is that there must be the use of an agreed dictionary to define the meaning of any words in the data items and how they should be displayed. ISO 13585. Parts Libraries provides the information model for such a dictionary, and a view of a prototype dictionary using ISO 13584 is shown here, derived from terms in the USA Department of Defense Military Handbook 5. The names of test methods are identified in the left-hand column. The upper panel on the right lists the names of properties that could be applicable to these test methods, and the lower panel defines the property that has been selected by the highlighting in the upper panel. ISO 13584 provides the basis for the dictionary of terms for modern cutting tools to support ISO 13399 cutting tool, data representation and exchange. The digital data may need to be communicated to unknown systems in the future, and the STEP technology provides the means for digital engineering data to be conserved. A framework for the conservation of information has been standardized as the Open Archival Information System, OAIS framework. Originally developed by NASA for data from space observations, it had now been endorsed by ISO for general use for the conservation of data as ISO 14721. The importance of the STEP standards for the data quality management in this framework is their role as testable specifications of the information. Then, by defining the syntax and the semantics of the information, the meaning of the data items is preserved independently from proprietary software in order to meet the requirements of preservation planning. The data representation standards, originally for engineering products, are also effective for digital materials information, since materials are products too. Key insights include the role of data context in validating property values, the importance of measurement methods for value interpretation, and the opportunity to extend AP235 beyond testing to cover full process modeling. The combination of a deep understanding and knowledge of materials and high expertise in digital information modeling has enabled the creation of ISO 10300 3-part 45 and its extension to AP235. This technology has been experimentally verified by use in several engineering testing and measurement situations. It is the 20th century equivalent of the standardization of screw threads and bolt sizes in the 19th century.